Usually when we talk about the math we learned in school, there's this expectation of absolute completeness.
Oh, for sure.
Like, we're taught to view it like a finished jigsaw puzzle. You learn the dot product for finding angles, you learn the cross product for finding perpendiculars, you learn matrices for transforming shapes.
And the teacher just points at the chalkboard and says, well, there it is. That's the toolbox.
Exactly. That is how space works.
Right. It's presented as a closed loop. I mean, we like our tools to be standard, neatly categorized into separate little boxes that just don't overlap, and we assume those tools represent the foundational truth of the universe.
But then you look closely at higher dimensional geometry. You look at how game engines process light and shadow, or you look at theoretical physics trying to map a black hole, and suddenly you realize that jigsaw puzzle we were handed is missing half its pieces.
Or the pieces are jammed together from entirely different puzzles.
Yeah, we are looking at a mathematical landscape that is fundamentally fractured.
The term mathematical muddy waters doesn't even begin to cover it. What we are taught as a unified, pristine system is actually, well, it's a collection of disconnected patches developed by different people at different times, often to solve very narrow, isolated problems.
And that is our mission today. We are staring at a massive stack of research texts, Grassman-Cayley algebra, exterior algebra, geometric algebra, and space-time algebra.
It's a lot.
It's a mountain. The goal is to completely demystify this towering wall of complex math for you. We aren't skipping the hard parts. We are not watering down the geometry.
No, definitely not.
If you're prepping to build a physics engine, or if you're just insanely curious about the actual raw fabric of reality, we are going to explore a hidden, unifying mathematical language today. A language that suggests the math we use every day is actually a fragmented, incomplete shadow of something much larger.
Right, we're going to unpack the definitions, the equations, and the underlying geometric reality of this big picture system. Because once you see it, you realize that this single framework connects the code, rendering a 3D video game directly to the equations governing Kerr black holes spinning in deep space.
And to Maxwell's laws of electromagnetism.
Exactly.
Okay, let's unpack this by going back to where this fragmentation actually started, because there's a real human tragedy at the center of this math. We have to rewind to the 1840s, to a German high school teacher named Hermann Grassmann.
Yeah, Hermann Grassmann might be one of the greatest unrecognized visionaries in the history of science. In the 1840s, he published a massive, incredibly dense work called the Ausdehnungslehre, which translates to the theory of extension.
Right.
His goal was breathtakingly ambitious. He wanted to develop what he called synthetic geometry. That means doing geometry entirely without coordinates.
Wait, let me stop you there, because doing geometry without coordinates sounds like trying to write a novel without an alphabet.
It does.
I mean, I was taught that to define a shape or a movement, you have to place it on an XYZ grid. You need numbers like 2, 5, 1.
But think about the universe itself, right? The universe doesn't have a giant glowing x-axis and y-axis floating out in space.
I guess not, no.
A grid is an arbitrary human scaffolding we impose on reality to help us calculate things. Grassmann realized that geometric objects, lines, planes, volumes, they have intrinsic properties and relationships that exist completely independent of any grid.
Oh, wow.
He wanted to create an algebra where the variables themselves represent the pure geometric shapes, and you can add, multiply, and transform them directly without ever breaking them down into separate x, y, and z numbers.
So instead of calculating the coordinates of point A and the coordinates of point B and using the Pythagorean theorem to find the distance, you just create a mathematical object that is the line connecting them, and the math processes the line itself.
That is the core of his vision. But it was met with absolute silence. The mathematical community in the 1840s completely ignored the Ausdehnungslehre.
The sources outline a pretty brutal reason for that, too. It wasn't just that Grassmann was a high school teacher without academic prestige. It was that the language he needed, linear algebra, hadn't really been formalized yet.
He was writing advanced poetry in a language the rest of the world was still trying to invent an alphabet for.
That's a great way to put it.
He was proposing a massive algebra of extended multidimensional quantities, but the mainstream mathematical community of his era was barely comfortable with the basic concept of vectors. They had no mental framework to process what he was offering.
Because Grassmann's unified system was left gathering dust, physics and mathematics had to keep moving forward. But they did it by stumbling down a deeply fractured path over the next century. Our timeline traces this perfectly. From roughly 1860 to 1890, William Rowan Hamilton comes along and pushes quaternions.
Right? Hamilton famously had a flash of insight while walking in Dublin and carved the quaternion equation into Brougham Bridge. Quaternions are a four-dimensional number system. They are absolutely brilliant for calculating 3D rotations, which is why spacecraft control systems still use them today.
But they're notoriously difficult to generalize to other dimensions. Right?
Exactly, and they're clunky for calculating basic linear movements.
So they were a very specialized tool. Yeah. And then in the 1890s, we get Josiah Willard Gibbs and Oliver Heaviside. This is where the math most of us know actually comes from.
Yeah, Gibbs and Heaviside looked at Hamilton's quaternions and essentially decided they were too complicated for practical engineering. They stripped quaternions down, threw away the parts they found philosophically confusing, and formulated standard vector calculus. They gave us the dot product to measure parallel alignment and the cross product to find a perpendicular direction in 3D space.
It's a bit like finding a hyperdrive from a disassembled spaceship, smashing it with a hammer, and turning the pieces into a really good combustion engine.
That's exactly it. Sure, the combustion engine works for driving down the street, but you've completely lost the deeper truth of how the universe travels between stars.
And that fragmentation only accelerated. In the early 1900s, Einstein's theory of relativity and Hermann Minkowski's space-time model required math that could handle curving geometry in 4 dimensions. Gibbs' vectors couldn't handle that smoothly.
No, they couldn't.
Ah!
So physicists adopted tensor calculus. Tensors are incredibly powerful, but their notation is an absolute nightmare of floating superscripts and subscripts that often obscure the actual geometric shape of what you're calculating.
You spend more time bookkeeping the indices than visualizing the physics.
Then, in the 1930s, Ellie Cartan developed differential forms. Cartan actually circled back and rescued a piece of Grassman's original algebra, specifically a tool called the outer product, and used it to do calculus on smooth, curving manifolds.
Look at this mess. I mean, we have quaternions handling rotations over in this corner. We have Gibbs vectors handling basic physics for engineers. We have tensors loaded with tiny indices for the relativity folks. And we have differential forms for the advanced topologists. The spaceship is scattered across 4 different disciplines.
And this isn't just an abstract history lesson. The Terathon software presentation by Eric Lengyel explicitly points out that this exact fragmentation is plaguing computer science today. Modern 3D graphics programmers are using all these separate pieces.
Like they use dot products for lighting angles, cross products for surface directions, scalar triple products for volumes,
Clicker coordinates for lines, and giant matrices to move things around. Lengyel notes they are doing this without knowledge of the connection among them.
They're memorizing an encyclopedic list of separate recipes without ever learning how to cook. If we want to fix this, if we want to rebuild Grassman's engine and see the universe natively, we have to start at the absolute bedrock of his system. We need to look at the wedge product.
The wedge product. It's also known as the outer product, and it's denoted by that upward-pointing triangle symbol, which looks like a little roof, a wedge.
Right.
This operation is the beating heart of Grassman's exterior algebra. To define it rigorously, as our source texts do, we have to start by imagining a vector space, which we will call V. We look at its tensor algebra, T of V. The exterior algebra is defined mathematically as a quotient space, T of V over J.
Hold on, we can't just drop terms like tensor algebra and quotient space without breaking them down. Let's ground this. A tensor algebra, T of V, is essentially the space of every conceivable combination of vectors multiplied together. You just keep sticking vectors together like Legos using a tensor product, creating infinitely larger and larger mathematical objects.
That is a perfect visualization. The tensor product is extremely permissive. It has almost no rules. It just links objects into endless chains. But to get the exterior algebra, we take that massive chaotic tensor space and we tame it. We apply a strict overriding rule. That's what dividing out by an ideal J means. A quotient space is like taking an infinite plane of numbers and folding it over on itself by declaring that certain things are equivalent. In this case, the ideal J acts as a universal filter, enforcing one bizarre law.
And that law is the square of any vector is always 0. Written out, it's V wedge, V equals 0.
Okay.
Now, I have to challenge this. If I drive 5 miles straight north and I multiply that by 5 miles straight north, you're telling me the math says I get absolute 0?
Yes.
My physics teacher would have failed me on the spot. Why does this geometry demand that something times itself equals nothing?
Because you're thinking of multiplication as scaling magnitude. You're thinking of 3 squared equals 9. But the wedge product isn't scaling, it's sweeping.
Sweeping.
I have to look at what a wedge B physically means. If you take a vector A and you wedge it with a vector B, you are creating a bivector. A bivector is a completely new category of mathematical entity. It's not a scalar, which is just a zero-dimensional number. It's not a vector, which is a one-dimensional line. A bivector represents an oriented two-dimensional area.
Oh, so it's the physical surface stretched out between the two arrows.
Specifically, it's the parallelogram formed by taking the line segment of vector A and sweeping it along the entire length of vector B. The space swept out by that movement is the bivector, a wedge B.
Okay, with that visual in mind, v wedge v equals 0 makes perfect, undeniable sense. If I take a vector v and I try to sweep it along its exact own path, I haven't swept out any area. I've just traced the exact same line twice.
Exactly. The 2D area created by sliding a line along itself is 0. The geometry demands the 0. And here is where Grassman's genius activates. If you enforce the simple visual reality that the square of any vector is 0, it completely dictates how different vectors must interact with each other. It forces a property called anti-commutativity.
This proof is laid out in the sources, and we are going to walk through it step by step because it's elegant. Let's take two different vectors, a and b. We add them together to make a brand new vector, which we'll just call a plus b. Now we take that new combined vector and we wedge it with itself, a plus b wedge all plus b.
And by our fundamental unbroken rule, sweeping any vector along itself creates 0 area.
Yeah.
So a plus b wedge a plus b must equal 0.
Right. Now we use basic algebra. The wedge product distributes. It expands out just like foiling binomial in high school algebra.
Yeah.
When we multiply out a plus b wedge a plus b, we get 4 terms. A wedge a plus a wedge b plus b wedge a plus b wedge b, and all of that equals 0.
But look at what we just expanded. The first term is a wedge a. The sweep of a along a, that's 0. The last term is b wedge b, that's also 0. Those terms completely vanish from the equation.
So the equation shrinks down. We're left with just the two middle terms. A wedge b plus b wedge a equals 0.
Now move the b wedge a to the other side of the equal sign. You get a wedge b equals negative b wedge a.
There it is, anti-commutativity.
It is a profound structural truth of the universe. The order in which you multiply vectors matters, and flipping the order flips the sign from positive to negative.
Geometrically, what does a negative area even mean?
It means the 2D area has an orientation. Imagine a clear pane of glass representing the plane. Sweeping vector A along vector B traces out the area in a counterclockwise direction, defining a top side of the glass.
Okay.
If you reverse the order and sweep vector B along vector A, you trace the exact same shape, but in a clockwise direction. You're now looking at the bottom side of the glass. The negative sign represents that reversed orientation.
And this logic scales up relentlessly. If we add a third vector, c, and we calculate a wedge b, wedge c, we're taking that flat 2D parallelogram and we are now sweeping it along a third direction in space.
Which creates a trivector, an oriented three-dimensional volume shaped like a parallel pipette. What's fascinating here is how this introduces the concept of a grade. The math organizes the universe into grades based on dimensions. In an n-dimensional space, the grade of an object called a k-vector is simply the number of independent vectors you wedge together to build it.
So a pure number, a scalar, is grade 0. It has no direction. A standard vector is grade 1. It's a line. A bivector, our swept area, is grade 2. A trivector volume is grade 3.
The algebraic rule is incredibly clean. If you wedge an object of grade p with an object of grade q, the resulting geometric object has a grade equal to p plus q. A grade 1 vector wedged with a grade 2 bivector yields a grade 3 trivector. You're physically adding dimensions of space together through multiplication.
But practically speaking, if someone is programming a physics engine, how do they calculate this? Do they have to draw parallelograms on a screen?
Not at all. The math provides direct numerical methods. Let's drop into 2D space r squared as the source details. We have two vectors, v and w. If you list their components and stack them into a 2x2 grid, creating a matrix A, the magnitude of the wedge product, v wedge w, is exactly equal to the determinant of that matrix A. You multiply that determinant by the basis bivector E1 wedge E2.
A basis bivector. That's like the fundamental pixel of area for that space, like taking the standard x-axis E1 and the y-axis E2 and wedging them to make a unit square.
Yes. And expanding to 3D space R cubed, we have 3 standard axes, E1, E2, and E3. From those 3 lines, we can construct exactly 3 fundamental planes, or basis bivectors. We wedge the first 2 to get E12. We wedge the first and third to get E13. We wedge the second and third to get E23.
And any 2D plane you could possibly draw in a 3D world is just a linear combination, a mixture of those three oriented basis planes.
Exactly.
We've built a robust, flawless vocabulary for constructing geometry. We start with points, we wedge them to make lines, we wedge lines to make areas, we wedge areas to make volumes. But that's only half of the story. This brings us into the deeper waters of the grassman algebra. Up until now, the wedge product has only been building things up. In the literature, this upward building process is formally called the join.
Right. If you have two vectors spanning different linear spaces, wedging them together joins them into a higher dimensional space that encompasses both. But grassman algebra is a complete ecosystem. For every action, there must be a mathematical reaction. It introduces the precise dual operation to the join. It introduces the meet.
Denoted by the symbol V, which looks like a downward pointing triangle. It's also referred to in the texts as the regressive product. The wedge points up and expands, the meet points down and contracts.
Exactly. While the wedge product builds dimensions up by combining spaces, the meet product finds their shared intersection, bringing the dimensions down.
To really wrap our minds around the meet, we have to grapple with the CSUN source text's explanation of dual bases. This is where it gets highly abstract. The text says we can express a k-vector in a dual basis containing all the unit vectors that are not used to compose the original k-vector.
Let's construct a 4D space to see this clearly. In a four-dimensional space, we have four basis vectors: E1, E2, E3, and E4. The dual of the vector E1 is defined as the geometric space made out of everything except E1. So the dual of the 1D line E1 is the 3D volume E234.
Oh, it's like looking at a photographic negative. If your object is a white dot on black paper, the dual is a black dot on white paper. The dual is the empty space left behind by the object within the total available volume.
That's a phenomenal way to conceptualize it. The mathematical mechanism handling this inversion is called the dual star operation, denoted by a star symbol. The sources define a critical, unbreakable bridge between the wedge and the meet using this dual star. The equation reads, the dual of alpha meet the dual of beta is exactly equal to the dual of the quantity alpha wedge beta.
Written symbolically, it's star alpha meets star beta equals star applied to alpha wedge beta.
Exactly.
So the meet is literally just the wedge product, but executed in the mirror universe of the dual space. Whatever builds up in the negative space must be the intersection in the positive space.
And because it's born from the wedge product, the meet follows rigorous anti-commutative properties, but those properties are dynamically tailored to the dimensions of the objects interacting. The CSUN text specifies this property. A meet B equals -1 to the power of jk times B meet A.
Translate that formula for me.
It means the meet of A and B is the same as the meet of B and A. But you might have to flip the sign, depending on the variables j and k. Those variables represent the steps, or the dual grades, of the objects. Depending on whether those dual grades multiply out to an odd or even number, the intersection might flip its orientation.
Let's shine a light on this with a physical analogy. We need a geometric translation of the meet.
Imagine two solid planes of glass in a 3D room. If you take the first plane and you calculate its meet with the second plane, the mathematical result is the single 1D line where those two panes of glass cut through each other. Plane meet, plane equals line. It algorithmically extracts the geometric intersection.
I want to push on that. What if I have a point and a line? How does the algebra know if the point is actually touching the line?
In incidence geometry, you use the wedge product to test this perfectly. A point is on a line if, and only if, quite wedge line equals 0.
Because if the point is already resting perfectly on the line, sweeping the point along the line's path creates absolutely no new geometric area. It's entirely redundant. Area equals 0.
Exactly. And through the duality theorem, this test is mathematically identical to saying point meet line equals 0. The join and the meet together provide a complete unified vocabulary for testing how every shape in the universe intersects and builds.
I notice the text keeps using the word copoint. It says duality exchanges points and copoints. We know what a point is. What on earth is a copoint?
It's entirely relative to the dimensions of the space you're working in. In any given n-dimensional space, a point is an entity of grade 1. A copoint is simply an entity of grade n-1.
The absolute maximum grade -1. So in a normal 3D room, a point is 1D. And a copoint would be 3-1, which is a 2D plane.
Correct. In 3D projective geometry, the mathematical dual of a point is a plane, and the dual of a plane is a point. Because of this, you can take any complex theorem in incidence geometry, literally cross out the word point and write plane, swap every join symbol for a meet symbol, and the resulting theorem will remain completely flawlessly true.
That feels like finding an exploit in the code of the universe. Now, looking further into the CSUN text, there's a monstrous equation listed under the alternative law. It looks terrifying, but the outline mandates we don't skip it. It reads, let A1, A2 up to ACB points. Let gamma 1, gamma 2 up to gamma hes be copoints. Then that quantity of all those points wedged with all those copoints wedged together, equals a massive signed sum of brackets. It mentions something called shuffles.
We must tackle the alternative law because it demonstrates the raw computational horsepower of this algebra. When a computer needs to find the intersection of massive, complex geometric structures, it can't just draw pictures. The alternative law equation is a machine for expanding the wedge product of a block of points with a block of copoints into a sum of smaller, easily calculable brackets.
The right side of the equation pairs things up. It groups the first point with the first copoint, the second point with the second copoint up to S, and then it takes the mean of whatever remaining points were left over.
Yes. But the mathematical engine running that process is the word shuffles. The equation explicitly states that it requires a sum over all shuffles over the 1 up to 1 k minus s split of the points A1 through AC.
What exactly is a shuffle over a split?
Let's use a physical deck of playing cards. Imagine you have a deck of 5 cards, numbered 1 through 5. These are your points. A shuffle in this context is a specific kind of mathematical permutation, a way of reordering the cards. You divide your 5 cards into groups based on the split. The split rule tells us to pull out individual cards, the 1, 1, 1 part, until we are left with a final group of size k minus s.
Let's say k is 5 and s is 2, so our final group size is 3. We pull out 2 individual cards and we are left with a block of 3 cards. Let's say that block is cards 3, 4, and 5.
A shuffle permutation dictates that you can rearrange the entire 5-card deck any way you want, but you must obey one absolute law. The cards within that final block of 3 must remain in their original increasing order relative to each other.
So I can mix the deck, so it reads card 3, then card 1, then card 4, then card 2, then card 5. Because even though they're separated, 3 still appears before 4, and 4 still appears before 5.
Exactly. That is a valid shuffle over the split. The alternative law formula demands that you take a signed sum of every possible valid shuffle permutation.
Where do the signs come from?
From the permutations themselves. If a specific shuffle requires an odd number of adjacent swaps to get the cards back to their original starting order, you subtract that term in the formula. If it requires an even number of swaps, you add the term. By algorithmically tracking these shuffles and swapping indices, the alternative law allows a computer to perfectly calculate complex geometric intersections without ever needing a visual coordinate grid.
It's the ultimate tool for a rendering engine. But Grassman's architecture doesn't stop here. We are about to blow the roof off the space we are working in. We need to look at the text from the Laver archives, which transitions us from vector spaces to affine spaces. Up until this point, we have been working inside the exterior algebra of a 3D vector space, which mathematically has 8 dimensions.
We should prove that 8-dimensional claim before we move forward. How many fundamental basis elements exist in a standard 3D vector space? You have exactly one scalar, representing pure magnitude. You have 3 separate basis vectors, representing the x, y, and z axes. You have 3 basis bivectors, representing the 3 fundamental planes. And you have 1 basis trivector, representing the 3D volume. Add them up. 1 plus 3 plus 3 plus 1 equals exactly 8 dimensions. The space of all pure vector geometry is 8-dimensional.
But the Laver text drops a structural bomb. It proves that the Grassman algebra, denoted G of E of a 3-dimensional affine space, is not 8-dimensional, it is suddenly 16-dimensional. We just doubled the size of our mathematical universe. Where do those extra 8 dimensions come from?
The expansion happens because of the fundamental difference between a vector space and an affine space. A vector space, V, is only concerned with direction and magnitude. In pure vector math, all arrows effectively start at a single universal origin point. You can slide them around to add them, but they have no fixed absolute location.
Okay.
An affine space, E, introduces the concept of rigid position. It consists of distinct points anchored in space.
Think of a vector space like a weather map, showing only wind currents. You see arrows showing which way the wind is blowing and how hard, but there's no map underneath. An affine space is putting the map underneath. Now, you don't just have a vector pointing north at 5 miles per hour. You have a vector pointing north at 5 miles per hour, specifically originating from the coordinates of Chicago.
That's a great analogy. The vectors in an affine space simply become the mathematical translations between the fixed points. To handle this immense jump in complexity, the Grassman algebra functor G of E applies a highly non-trivial structure to the affine space. It introduces an entirely new mathematical machine, the boundary operator, denoted by the partial derivative symbol, del.
Grassman originally named this concept the Ausgleichung, an old German term roughly translating to dodging or evasion. So what does this all mean? What does this boundary operator actually do to the geometry?
The Lauder text explains that the unique affine linear map from the space E to the single-point space induces a linear weight functional. Using a structure known as the Koszul complex, this linear functional is extended across the entire graded algebra to become the operator to lim.
We need to pull that out of the textbook and put it in the real world. You mentioned the Koszul complex extends a functional. Basically, we have a mathematical machine that can eat a complex geometric object and systematically spit out its exact boundary.
Right.
If I feed the del operator a solid 2D triangle, the machine strips away the interior and spits out the 1D perimeter, the 3 connected line segments. If I feed the machine one of those 1D line segments, it spits out the 2 0D endpoints.
Exactly. It systematically reduces the grade of the object to find its edges. And this boundary operator obeys 2 massive, universe-defining rules. First, it satisfies a signed Leibniz product law. This means it interacts with the wedge product similarly to how the product rule operates when you're doing basic calculus derivatives. Second, and vastly more important, the operator has square 0. Del squared equals 0.
Let me make sure I'm visualizing this correctly. The boundary of a boundary is 0.
Yes. Let's trace it. The boundary of your solid 2D triangle is the 1D line perimeter. Now apply the operator again. What is the boundary of that 1D perimeter loop?
Well, the loop is closed. It connects back to itself. There are no dangling endpoints, so the boundary of the loop is nothing. It's 0.
Del of the triangle equals 0. This simple equation, del squared equals 0, is the absolute foundational bedrock of 2 entire fields of advanced mathematics homology and algebraic topology. It defines what a closed shape actually is.
So how does this operator organize our new 16-dimensional affine space?
In the 16D algebra, the elements P, where del P equals 1, are mathematically defined as the rigid points of the original space E. Conversely, the kernel of the operator, which means all the elements X where del X automatically equals 0, that subspace is precisely the exterior algebra of the translation vectors we talked about before.
The original 8-dimensional space of pure direction vectors is nested inside the 16-dimensional affine space. The 8D space acts as the engine, the translation mechanism, moving the rigid points around inside the larger 16D structure.
The text also explores exact sequences. It states a fundamental theorem. If del X equals 0, then X equals del of P wedge X for any point P.
Break that sequence down.
If you have a geometric object X that has no boundary, like a floating closed loop of 1D vectors in space, you can always mathematically express that loop as the boundary of a higher dimensional object.
Yeah.
You simply wedge an arbitrary point P with the loop X. Geometrically, this stretches a 2D surface from point P down to every part of the loop, forming a 3D cone.
And if you apply the boundary operator to that cone, it strips away the cone's surface and what's left at the base. The original closed loop X. It's a flawless, self-contained logic system. It perfectly integrates position, translation, and physical boundaries into one 16-dimensional structure.
It is staggering in its elegance. But Grassman's exterior algebra, even with the addition of affine spaces and boundaries, is still harboring a fatal flaw. A flaw that kept it from overtaking standard physics in the 19th century.
You can't divide.
You cannot easily divide by a vector in the exterior algebra. And if you are an engineer or a physicist trying to solve complex equations of motion, you absolutely must be able to divide. You have to invert operations to isolate variables.
So the evolution of the math couldn't stop with Grassman. It had to mutate again. It evolved into what we now call geometric algebra. This was pioneered by the English mathematician William Kingdon Clifford, who realized he could fuse Grassman's exterior algebra of spaces with Hamilton's quaternions of rotation.
And the engine running Clifford's geometric algebra is the geometric product.
The geometric product is the holy grail of this entire mathematical journey. It's denoted in the simplest way possible, by writing 2 multivectors right next to each other, no dot, no wedge, just a B. It achieves what everyone thought was impossible. It generalizes complex number and quaternion multiplication to multivectors of any grade and any dimension.
How does the geometric product fundamentally differ from the wedge product we spent so much time on? What changes at the bedrock level?
It all comes back to that quotient rule, the ideal J we discussed earlier. Remember how the exterior algebra enforced the rule X tensor X is equivalent to 0?
The sweeping of a vector along itself creates 0 area?
Right. Sweeping a line along its own path annihilates the area.
The geometric product alters that foundational rule.
Hmm.
In the geometric algebra quotient space, we retain the anti-commuting nature for orthogonal vectors. So perpendicular parts still flip signs. X tensor y is equivalent to negative y tensor x.
Okay.
But for a vector multiplied by itself, we declare that x tensor x is no longer 0. It is now equivalent to 1, or more accurately, it is equivalent to the square of the vector's physical length, its magnitude, the absolute value of x squared.
So duplicate tensor terms don't annihilate. They collapse into a pure scalar number.
Yes. Visually, the geometric product AB calculates two things simultaneously. It calculates how parallel the two vectors are, which is a scalar number, identical to the traditional dot product,
Yeah.
and it calculates how perpendicular they are, which is the oriented bivector area, identical to the wedge product.
AB is the sum of a scalar and a bivector.
You are adding a zero-dimensional number and a two-dimensional area together in the same equation. That sounds insane, like adding apples and square feet. It seems unnatural until you realize complex numbers do the exact same thing by adding real numbers to imaginary ones. It creates a richer, multifaceted object. And because the square of a vector now yields a non-zero scalar magnitude, we unlocked the ultimate superpower. We can divide, we can invert multivectors.
The source texts provide the incredibly simple formula for this inversion. If you want to find the inverse of a vector A, written inverse, you just take the vector A itself and divide it by its magnitude squared. A inverse equals A divided by the absolute value of a squared. It requires no massive matrix calculations. It's just division by a scalar.
It's simple, but its geometric implications are profound. The texts provide a stunning example of a concept called rejection. What happens if we take our wedge product, a wedge B, that 2D parallelogram area, and we geometrically multiply it by the inverse of A? We calculate A inverse times a wedge B.
Okay, let's walk through the physical mechanism of this formula. The text states A inverse times a wedge B equals B minus B parallel to A.
Multiplying the inverse of A into the bivector area mathematically extracts the vector B, but it cancels out the A direction entirely. It literally subtracts the portion of vector B that was running parallel to A.
It's like taking vector B and peeling away its shadow. If B is casting a shadow onto line A, the geometric product strips that shadow away. You are left exclusively with the part of vector B that is pointing dead perpendicular to A. The text labels this pure perpendicular leftover as B perpendicular to A.
This is the orthogonal rejection of B from A. The source is careful to note that this doesn't invert the wedge product in every mathematical sense because it destroys the parallel information, but it's an incredibly powerful, geometrically true operation. We can now algebraically manipulate 3D space by fluidly adding dimensions with the wedge and dividing out dimensions with the inverse.
Which brings us crashing back into the practical world of modern computer science. We mentioned Eric Lengel's presentation at the Game Developers Conference earlier. Lengel is standing in front of a room full of the best 3D engine architects in the world, the people writing the physics for the biggest video games on Earth. And he is telling them that the standard math they use to calculate lighting and shadows every single day is a convoluted hack.
And he backs it up with proof. Think about how a 3D game calculates lighting. Light hit the polygon, and the engine needs to know which way the surface of that polygon is facing. It uses a normal vector, an arrow pointing straight out of the surface.
But when the polygon rotates or stretches, the normal vector has to move with it.
Exactly. The standard patched-together math dictates that the programmer must multiply the normal vector by the inverse transpose of a matrix.
A massive grid of numbers that requires heavy computing power to invert and flip. And if you ask most programmers why they use the inverse transpose, they'll tell you because it works. It's just a recipe they memorized.
But geometric algebra reveals the truth. Normal vectors aren't actually vectors at all. They are bivectors, disguised as vectors. They represent the oriented 2D surface area of the polygon itself.
Oh, wow.
If you stop treating them as 1D arrows and start treating them as 2D bivectors using the geometric product, the math natively handles the stretching and rotation. The bivector transforms perfectly on its own. The computationally expensive inverse transpose matrix hack vanishes completely.
Langell shows the same thing happens with Plucker coordinates. Programmers use this highly complex 6-coordinate system just to represent where a 3D line is floating in space. But in geometric algebra, you don't need 6 coordinates. A 3D line is simply the wedge product of 2 points, or alternatively, it is the meet of 2 planes.
It is natively built right into the algebra. The dot product, the cross product, the scalar triple product, all the fragmented pieces of the spaceship are finally reassembled into one engine, the geometric product.
Langell's presentation slide summarizes it perfectly. Understanding the big picture provides deep insights into seemingly unusual properties. Knowledge of the relationships among these concepts makes better 3D programmers.
When you stop fighting the fragmented math and start speaking the native language of the geometry, the physics become fluid.
Okay, so we've fixed the lighting in video games. Let's aim a little higher. Let's fix the physical universe. We need to elevate this mathematical architecture into theoretical physics. We are going to look at the force that allows the light in your room to exist and the screen you're looking at to function electromagnetism. To get there, we first step into the world of Élie Cartan and his differential forms.
In the early 20th century, Élie Cartan realized the power of Grassman's exterior algebra and adapted it to perform calculus over smooth, curving manifolds, spaces that bend and warp. He formalized objects called differential forms.
In his system, a one-form is roughly analogous to a field of vectors, mapping line integrals. A two-form maps flux across surfaces, analogous to a field of bivectors. A three-form maps density within a volume.
And Cartan maintained the wedge product to combine these forms. But he formalized a very specific commutation rule for how forms multiply. The electromagnetics text gives us this exact equation. Alpha wedge beta equals -1 to the power of PQ times beta wedge alpha.
Let's decode that formula. The variables P and Q represent the degrees, or the grades, of the two differential forms you are wedging together. The rule dictates that the wedge product of two forms will commute normally, meaning order doesn't matter, and A wedge B equals B wedge A, unless both of the forms have an odd degree.
So if P is an odd number and Q is an odd number, like wedging a one form with another one form or a one form with a three form.
Precisely. If and only if both are odd, the exponent PQ becomes an odd number, and -1 to an odd power remains -1. The product anti-commutes. The sign flips. If even one of the forms is an even degree, like a two-form wedged with a one form, the product commutes perfectly with no sign flip.
Cartan used this specific graded wedge math to completely rewrite the most famous equations in physics, James Clerk Maxwell's laws of electromagnetism.
The standard Maxwell equations are notoriously complex to look at. Physics students spend semesters untangling them. The Maxwell-Ampere law relates the curling magnetic field to the electrical current. Del cross H minus the partial derivative with respect to time of D equals J.
The Gauss law relates the diverging electric field to the charge density. Del dot D equals epsilon. They use separate vector operations, cross products, dot products, curls, and divergences. It treats electric and magnetic fields as fundamentally different mechanical behaviors.
But Cartan's differential forms slice right through the complexity. He rewrites the vector H, the magnetic field, as a one form. He rewrites the vector D, the electric displacement, as a two form. And suddenly those chaotic equations compress into this. D wedge H minus the partial derivative with respect to tau of D equals J, and D wedge D equals epsilon.
The messy curls and divergences are entirely replaced by a single elegant operator, the exterior derivative D wedged with the physical field. Equation 4.18 becomes an equation purely between two forms, natively relating the magnetic field to the current density two-form J.
And equation 4.19 becomes an equation purely between three forms, natively relating the electric field to the charge density three-form epsilon. It visually proves that electricity and magnetism aren't different phenomena. They are literally just different geometric grades, different dimensional shapes of the exact same underlying reality.
Differential forms were a massive upgrade over Gibbs's standard vector calculus.
Oh.
But as we look at our final source, the massive Vixora paper on relativistic physics, we realize that even differential forms are not the final truth. Forms still artificially separate the electric and magnetic equations. To reach the ultimate unification, we have to introduce space-time algebra, or STA.
Developed by physicist David Hastings in the 1960s and heavily championed by the Cambridge Geometric Algebra Research Group, space-time algebra takes Clifford's geometric product and applies it directly to the four-dimensional fabric of the universe.
It moves us from a standard 3D space into a 16-dimensional flat Minkowski space-time algebra. And we need to explicitly define the building blocks of this space because they dictate how reality works.
Let's count them out. What are the 16 dimensions of space-time algebra?
You start with exactly one scalar. This represents pure magnitude, or a time-like interval. Then you have four basis vectors, denoted gamma 0, gamma 1, gamma 2, gamma 3.
These represent the four cardinal directions of space-time. Gamma 0 is the time-like vector pointing into the future. The other three are the space-like vectors mapping x, y, and z.
And because we are in Minkowski space-time, the Pythagorean geometry is slightly warped. Time acts differently than space. The square of the time vector gamma 0 squared equals a +1. But the square of any spatial vector, like gamma 1 squared, equals a negative 1.
Correct. The metric signature handles the difference between space and time. Now, from those four basis vectors, we wedge them together in pairs to get six basis bivectors. These represent the six fundamental planes of rotation in 4D spacetime.
We wedge them 3 at a time to get 4 trivectors. And finally, we wedge all 4 vectors together to create exactly one pseudoscalar, representing the fully oriented 4D hypervolume of spacetime itself. Add those up. 1 scalar, 4 vectors, 6 bivectors, 4 trivectors, 1 pseudoscalar, 16 dimensions.
And here is the absolute pinnacle of this mathematical journey. We mentioned Maxwell's four complicated equations. Cartan's forms compress them into two. In space-time algebra, using the geometric product in this 16-dimensional space, all of electromagnetism compresses into exactly one single multi-vector equation.
Del F equals J.
Three symbols describe all of light, electricity, and magnetism. Del F equals J. I need you to break down every single component of this visually. What exactly is del?
Del is the spacetime Dirac vector derivative. It is a single unified vector operator that contains all the partial derivatives for both time and the 3 spatial dimensions. It measures how things change across the entirety of spacetime.
Okay, what is F?
If we connect this to the bigger picture, F is the electromagnetic Faraday field. In standard physics, we are taught that electricity is a vector and magnetism is a separate vector. In STA, F is not a vector. It is a pure geometric bivector. It is defined algebraically as F equals E plus IB.
The electric field E plus I times the magnetic field B.
Yes, the electric and magnetic fields are no longer separate entities. They are simply different geometric components of one single 4D surface area, the bivector F. The I in that equation is the pseudoscalar, the 4D hypervolume we mentioned. Multiplying by I acts as a duality operator. It perfectly rotates the magnetic field into its correct perpendicular orientation within the 4D space, so it can seamlessly add to the electric field.
And finally, what is J?
J is the spacetime current vector. It elegantly combines the scalar charge density and the 3D moving current density into a single 4D direction arrow.
So the equation reads, the geometric derivative of the Faraday bivector equals the spacetime current vector. Del F equals J. But how can one equation solve for 4 different things simultaneously? How does the math separate back out?
It uses the precise grade selection rules of the geometric product. Look at the left side of the equation. Del F, you're multiplying a derivative vector, del, which is grade 1, with the Faraday field, F, which is a bivector, grade 2. According to the rules of geometric algebra, multiplying a grade 1 object by a grade 2 object results in a mixed grade multivector.
Wait, so the single act of multiplication natively splits the output into a 1D vector part and a 3D trivector part.
Exactly. It produces a dot product part, grade 2 minus 1 equals 1, and a wedge product part, grade 2 plus 1 equals 3. And look at the right side of the equation. J is purely a vector. It is grade 1. It has absolutely no trivector part.
Therefore, for the equation to be mathematically true, the vector output of del F must equal J.
Yeah, the trivector output of del F must equal exactly 0. When you extract those two separate grade equalities from the one equation, you instantly recover the full Maxwell laws.
The Vixra paper explicitly notes something crucial here. The totally natural unification achieved in STA cannot be obtained by means of differential forms. Differential forms cannot multiply mixed grades like this. They can only wedge or take derivatives.
The geometric product is the only mathematical operator in existence that dynamically combines the dot product and the wedge product into a single invertible operation, allowing this total unification.
And the 16-dimensional architecture STA doesn't stop at electromagnetism. It scales directly into Einstein's realm of general relativity. It tackles gravity. The paper points out that in standard tensor calculus, calculating the curvature of a black hole requires pages of messy indices and things called Christoffel symbols.
Christoffel symbols are incredibly tedious mathematical bookkeeping terms. In standard calculus, because you are using an arbitrary coordinate grid to map a curving space, you need these extra symbols just to track how your grid lines are bending relative to each other. They don't represent physical forces, they just manage the distortion of the map.
But spacetime algebra doesn't use an arbitrary map. It uses the intrinsic geometry of the objects themselves.
Because of that, STA gives Einstein's curvature tensor a new unitary form. Using bivector variables instead of coordinate indices, STA allows for astoundingly compact solutions. For example, the Riemann curvature tensor R for a standard static black hole reduces to a single line. R of B equals negative m times the quantity B plus 3 x0 b x0, all divided by 2 r cubed.
I want to translate that from algebra into physics. It basically says the curvature of space caused by the black hole depends on the mass m, divided by the distance cubed, r cubed, and then multiplied by this bivector interaction b and x0.
B is your bivector variable, mapping the plane of orientation. And x0 is a relative unit radial vector. The formula isn't tracking points on a grid, it is calculating exactly how the mass of the black hole twists and scales the fundamental planes of space around it.
And the paper shows this exact same compact bivector math easily maps Kerr black holes that are actively spinning, dragging the fabric of spacetime with them in a vortex. But perhaps the most profound achievement in the relativistic physics source is how STA solves the energy momentum problem.
In the standard tensor formulation of general relativity, defining the exact energy contained in the gravitational field itself is famously problematic. The calculated energy often shifts and changes depending on which arbitrary coordinate system the physicist chooses to use. It lacks local gauge equivalence. It's a mathematically messy approximation.
But spacetime algebra fixes it using a bivector-valued superpotential.
Yes, STA allows for a position gauge invariant canonical split of Einstein's equations. Because STA calculates energy using the intrinsic, unchangeable geometry of bivectors rather than relying on an arbitrary, flexible coordinate grid, the resulting energy-momentum tensor is totally coordinate independent.
The energy remains mathematically true no matter how you look at the system. It strongly suggests that the physical universe operates fundamentally on the laws of geometric algebra.
It really does.
Let's step back and look at the absolute sheer scale of the journey we just took. We started in the 1840s with Hermann Grassmann, a high school teacher who dreamed of a coordinate-free synthetic geometry, only to be ignored because the world wasn't ready.
We watched as physics splintered, grabbing pieces of his vision to build quaternions for rotation, vector calculus for standard physics, tensors for gravity, and differential forms for topology.
We rebuilt his system from the ground up. We proved why the square of a sweeping vector must be 0 to encode 2D area, which forces vectors to anti-commute.
We mapped the Grassmann-Cayley algebra, uniting the upward building join with the intersecting meet, finding the dual spaces of reality and calculating exact intersections using the algorithmic shuffles of the alternative law.
We expanded our universe from an 8-dimensional vector space to a 16-dimensional affine space just by acknowledging position and introducing the boundary operator del, the mechanism that strips shapes down to their topological closed loops.
We discovered the geometric product, which finally allowed us to divide by multivectors, calculating orthogonal shadow rejections, and instantly rendering the clunky matrix hacks of modern 3D game engines obsolete.
And we ascended to spacetime algebra, where the 16 dimensions of flat Minkowski space compress all of Maxwell's laws of light and electricity into one beautiful equation, del F equals J, and provide the cleanest coordinate-independent map of black hole curvature ever theorized.
It is a profound unification of thought.
As we wrap up this massive deep dive, I want to leave you with a final, slightly mind-bending thought inspired by looking at all these sources together. If you look around the room right now, you are conditioned to think of the universe as being filled with things. You think of solid physical objects, of particles bouncing off each other, of invisible magnetic force fields acting like a physical substance pushing through the air.
We instinctively assume that the space itself, the 3D manifold, is the foundational reality, and the math is just a descriptive language we lay over the top of the substance to track its movement.
But if you look at the deep mathematical theory underlying Grassmann numbers, it hints at something radically different. In advanced applications, mathematicians sometimes contemplate a mathematical situation where they completely and intentionally ignore the existence of any underlying physical manifold. They throw away the space.
They simply contemplate abstract objects that follow the anti-commutation rule of the wedge product, forming a pure algebra. They build the entire structural behavior of the system from nothing but the rigorous rules of logical relation. No physical space required.
If spacetime algebra and Grassmann numbers can perfectly describe quantum physics, the exact angular spin of a photon, the gravity well of a Kerr black hole, and the topological boundary of a simple triangle by using only the abstract algebraic rules of anti-commutation and geometric products, what if reality isn't made of substance at all?
What if the geometry isn't describing the physical universe? What if the geometry is the universe?
What if the universe is, at its fundamental, absolute root, purely made of algebraic relationships, Just raw, unadulterated mathematical logic, interacting with itself, manifesting to our human brains as the illusion of physical space and solid matter. We started this deep dive talking about the expectation of absolute completeness, the comfort of holding a finished mathematical jigsaw puzzle. But maybe the deeper truth is there are no puzzle pieces, there are no edges, there is only the math. Thank you for joining us on this incredibly deep dive. Keep exploring the geometric nature of your world.